Now that we've been introduced to directional derivatives, let's apply some with some actual functions here. So recall, we have two ways that we've learned to look at directional derivatives. One's if the vector is given in terms of components, and the other is if the vector is given in terms of an angle. So the first one is we have some function here, and we want to look at the directional derivative at this point. So how's it changing at this point in space, and how's it changing in a particular direction at this point in space? So let's see if we can't follow through. So recall, to get this, we need to find these partials with respect to x and y. So no matter what we do, we have to find those partials. So let's find fx. Now this is maybe better written as and y is constant here, so we're really only taking the derivative of this. So you bring down the negative 1, you end up with negative y, x plus y to the negative 2. But if we take the derivative of the inside, again, y is constant, derivative of x is 1. So that leaves us with negative y for x plus y squared. So then if we get fx at 3, 0, we just have 0, because 0 on top, no problem. Okay, well now the derivative with respect to y, well, to do that, this time we have something in the numerator and the denominator, so something like a quotient rule makes the most sense. So we do low derivative of high minus high derivative of low. Again, that's constant, so this becomes 1 over low squared. So x plus y minus y gets me x, or x plus y squared. Okay, so then we have to find the partial at 3, 0, which gets me 3 over 3 plus 0 squared, so 9, 3/9, which is really just 1/3. Okay, so now I have these two partials, and I need to multiply it by this. This is already a unit vector. So in this particular case, we have the directional derivative in the direction of v, not in u. Notice our original thing writes u, but we want to write it to make sure we match the term here. So then we take this cosine theta, so that's 0, cosine of negative pi over 6, plus 1/3 sine of negative pi over 6. Well, that's 0, clearly. Negative pi over 6, sine of that is negative 1/2, so that gives me negative 1 over 6. Okay, so that's our first one. Let's do a second one. Same process. So let's go ahead and check. This is v. This is already a unit vector, so we're in good shape. We can use this function. So let's start writing it out. Partial with respect to x is just 3 minus 4y. And the partial at that point is 3 minus 8, so we end up with negative 5. The partial with respect to y is negative 4x plus 9. Plugging in gets us a positive 5. Simple enough. So then when we evaluate here. Let's write it in terms, it doesn't matter, but I'm going to try to follow the form here. So it's actually 3/5 times -5 plus 4/5 times +5. Well, that's just -3. That becomes +4. All that work just to get 1. And then finally, let's take a look here. So let's take some partial derivatives. Actually, before we do that, let's look at this thing. Okay, so we want to go in the direction of PQ. So we're starting at the origin and we're ending at this point, 2, 1. So if I constructed some sort of vector V out of that, or rather just the vector PQ, it'd be 2, 1. Well, that's not a unit vector. So to do that, we have to get the magnitude. To solve this, we need to get the magnitude of PQ. Okay. So that tells me that I'm going to call it V, which is the unit vector in the direction of PQ, is that 2 over the square root of 5, 1 over the square root of 5. So this is what we'll have to use in this equation. So with that out of the way, let's go ahead and compute some partial derivatives. Partial with respect to x. Okay, well that's a constant. Derivative of sine of x is cosine of x. So the partial at the origin is e to the 0 cosine of 0. Well, anything to the 0 power is 1. Cosine of 0 is also 1. So that gets me a 1. Partial of y, partial with respect to y. All right, well, that's treated as a constant. Derivative of e to the y is e to the y. So the partial at the origin is e to the 0 sine of 0. Well, that's just 0. So then going through, we fill this out, again using this formula. So the directional derivative, or the derivative in the direction of PQ. Now I do want to point out something here. I use PQ even though I wrote V as this. This is very explicit. This is fine because this terminology implies that you have used the formula correctly. So if you see this written somewhere, or if you're eventually writing a paper or doing some sort of write-up, this right here automatically implies that I've done the appropriate calculations and gotten a unit vector. It's simply saying in the direction of PQ. So we don't have to worry about that. So that at the origin is, we have to take the components here, 2 over the square root of 5 times 1 plus 1 over the square root of 5 times 0, which is 2 over the square root of 5. And those are some examples of how to compute directional derivatives.